Section 2.5 is about graphing rational functions. Now, we've been working with polynomials so far, and we've talked previously about how we can build functions out of other functions by combining them via arithmetic or composition. Now, with the arithmetic operations, if I had two polynomials and I added them, or subtracted them, or multiplied them, I'd just have another polynomial. But if I divide them, I might get something that looks like this. And this is not a polynomial because now we've got some x's in the denominator. This is what we call a rational function. Just like rational numbers, it has that word ratio in it that tells us it's a fraction. And a rational function is just a fraction where the top and the bottom are polynomials. Now, in graphing this, I'm going to start by just working through an example. And then in the next video, we'll talk about sort of what the steps are to follow step by step. The book has a list of steps. I have a list of steps. They're almost the same, although I include one step that I think is really important. The book usually does this, but they don't list it explicitly as another step. We've seen in our study of polynomials that finding where things are zero, and therefore having things in factored form, is very, very useful. So the very first thing I want to do when I have a rational function is I want to factor both the top and the bottom. So if I look here, I could try to unfoil that. That looks like I'd have to have an x and an x. In order to get 2, I'm thinking we need a 1 and a 2. Looks like both positive. Let's see, x squared, 2x plus x gives me 3x. 1 times 2 gives me my 2. Fabulous. Now the bottom, that's a difference of 2 squares because 1 is 1 squared. So I can factor that as x plus 1 times x minus 1. And now I can notice there's an x plus 1 on both the top and the bottom. Now, almost always, that's going to just reduce to 1. If x is 5, that becomes 6 over 6, and 6/6 is 1. The only time that wouldn't reduce to 1 is if x was negative 1, because that would make both the top and the bottom 0. I can actually see by having that x plus 1 in the denominator that negative 1 is not in the domain of this function. But as long as x isn't negative 1, this is going to be the same non-zero number on top and bottom, and I can cancel it. I just want to make sure that when I cancel it, I don't change the domain. So I'm going to explicitly record that x can't be negative 1. So there are two values that are not in the domain of this function. In the factored form, I can see they would be negative 1, which would make this factor 0, and 1, which would make this factor 0. In the reduced form, I can see 1 would make the denominator 0, and I just have to explicitly write x is not allowed to be negative 1, because I've chosen to cancel that factor so that I'm no longer writing it. That gives me a much simpler function to work with. I'm just not allowed to plug in negative 1. Okay, so that's usually the first thing I do, is I write the top and the bottom factored, get my fraction in lowest terms, and if I cancel anything, that means I'm recording those restrictions on my domain. Now, since I've just been thinking about the domain, when I go to graph, I will usually start with the things that are not in the domain. And here, we said we've got two numbers that are not in the domain, 1 and negative 1. And they're actually going to be represented graphically very, very differently. Because 1 still makes the denominator 0 even when this fraction is in lowest terms. Negative 1 does not. If I didn't record that restriction there, you'd think you could plug in negative 1. So let's take a look at what happens near 1. Nothing happens at 1 or negative 1 because I can't plug in either one. But near 1, as I got close to 1, the bottom is going to be getting close to 0. So the bottom's getting super, super small. And the top is going to be getting close to 1 plus 2, which would be 3. So what happens when you take something that's close to 3 and you divide by something really, really small? Well, when you divide by something small, you get something big. Let's just think about it. If I had 3 divided by 1, that's 3. 3 divided by 1/100th becomes 3 times 100 becomes 300. 3 divided by 1/1,000,000th, now we're getting a little bit smaller, that becomes 3 times 1 million. That's 3 million. We're starting to get big. And my numbers are getting arbitrarily close. As x gets close to 1, x minus 1 is getting arbitrarily close to 0. So as the denominator gets really small, the result gets really, really big. What that tells me is that at 1, we're going to have a vertical asymptote. So that our y values are going to be going off either to infinity or to negative infinity. So I'm just going to draw in that dotted line at 1. Okay. Now, negative 1 is also not in the domain. And if you've just looked at this form, you might be tempted to put an asymptote at negative 1. There's not an asymptote at negative 1. Because the graph of f of x, this function here, is going to be exactly the same as the graph of this, except that it doesn't have a point at negative 1. If I were to graph this, if I were to call this function g of x is different from f of x. F of x is g with that added restriction. G is just that fraction without the restriction. This would have a point at 1. If I plugged in 1, I'd get negative 1. If I plugged in negative 1, I'd get 1 over negative 2. So g of negative 1 is negative 1 plus 2 over negative 1 minus 1. That's going to be 1 over negative 2, or negative 1/2. So this function without the restriction would have a point at negative 1/1/2. F is exactly the same except there's no point there. So I'm going to come over here to negative 1, negative 1/2, and there's going to be a hole in the graph there. Okay. So there isn't a point there. But what's very significant about drawing the hole is once I've plotted some significant points for this function, we're going to play connect the dots. As I play connect the dots, my function has to come arbitrarily close to this location, so that if I didn't know better, I'd think there was a point there. The behavior of the function close to this point has to lead me to expect that there would be a point there. So you'll never see in a graph a hole just hanging out like it is right there. Eventually, a hole will always have a path leading to it, and in this case also away from it, saying, hey, I expect there to be a point there based on the nearby behavior. Okay, so those are the two values that are not in my domain. Those are the values that would make the denominator 0. Let's take a look at what makes the numerator 0. Okay. Now, I've already dealt with the negative 1. That made both the numerator and the denominator 0. We've already plotted our point here. So the only thing I haven't dealt with is what makes the top 0 when it's in lowest terms. And x plus 2 would equal 0 if x equals negative 2. Now, that would make the top 0. It doesn't make the bottom 0, because we've already dealt with the numbers that make the bottom 0. So that tells me that's going to be a location of an x-intercept. So at negative 2, 0, we're going to be on the x-axis. All right, if we're finding intercepts, let's go ahead and find the y-intercept as well. Okay. Now, to find the y-intercept, we simply plug in 0. So f of 0, and I can choose. I could plug into this. Since 0 is not negative 1, I could also plug into this. So it's a little bit faster, but not much. I'm going to get 2 over negative 1 either way, and that's just negative 2. So I know I'm going to have a point. My y-intercept is 0, negative 2. Okay. So I dealt with the values that are not in the domain. In this case, that gave me a hole and a vertical asymptote. And then I've dealt with my intercepts. Okay. So what I get when I plug in 0, and what makes the top of my fraction 0, but not the bottom, because that's what will make the output of this fraction equal to 0. Okay, next I'm going to deal with the end behavior. So what happens as x goes to infinity, and what happens as x goes to negative infinity? Now, I know what happens for just the top. That's going to go off to infinity, because the top is a polynomial dominated by its lead term. And the denominator is a polynomial. It's dominated by its lead term. That's also going to infinity. But I can't, in general, deal with just that. I can't assume that those infinities are going to be the same size. In this case, my lead terms are actually the same. But the rule is, just like a polynomial is dominated by its lead term, a rational function is going to be dominated by the fraction of its lead terms as we go off to infinity or negative infinity. In the middle, for moderate sized values, all these other terms are going to be important. But as we plug in really, really big stuff, whether it's really big and positive or really big and negative, f of x is going to behave approximately like x squared over x squared. It's going to behave like the fraction of its lead terms. And of course, if we're going off to infinity or negative infinity, x isn't 0, so I could just cancel this, and this would be 1. So I can say, as x goes to infinity, f of x goes to 1, and as x goes to negative infinity, f of x goes to 1. So really far out on the graph, the y values of my function are going to be getting really, really close to 1. When I have something like that, where the end behavior is that my y values are approaching a finite number, we're going to have a horizontal asymptote. Okay, excellent. So I know when I play connect the dots, and I'm then going really far to the right, I've got to ultimately be getting close to that horizontal line. Same thing on this side, I've got to be getting close to that horizontal line. Okay. All right, so with asymptotes, a vertical asymptote you can never cross. That's because we have this thing called the vertical line test. I'm graphing a function here. If I were to cross this, I'd say my y values were at this height where I crossed it, wherever that was, but then I wouldn't be going off to infinity or negative infinity, I'd be at that finite height. So you'll never ever cross a vertical asymptote. It is possible to cross a horizontal asymptote. And so I do want to check for that. So I'm going to try and see, do we ever cross that horizontal asymptote? Now, that's something that the book says you need to check for every single time. Sometimes I might say it's okay, you don't need to check. Read the directions carefully. Okay, if I ask you to check for crossing a horizontal asymptote, I want to see the work checking to see whether you cross that horizontal asymptote. But these are very time-consuming problems, and when you get to calculus next semester, you're going to have some other techniques that are going to make it fairly obvious whether you do or don't cross the horizontal asymptotes without having to check directly. So I'm a little bit less concerned with that skill. I'm going to go ahead and check that in this case. But on exams and quizzes where I'm writing the directions, read and see whether I explicitly ask for that or not. If I don't explicitly ask for it, you don't need to check for it. As you're doing the homework, you're following the directions in the book, and they do generally ask you to check for that. Okay. So how would I check to see whether we cross a horizontal asymptote? Well, that would mean that the y value of my function would have to equal 1. So I'd be setting f of x equal to 1 and trying to solve that. Now, it's entirely possible that I'm going to get no solution. If I get no solution, then we never touch this asymptote. If I do get a solution, that's where we do touch the asymptote. Okay, this video has been going for a while, so I'm going to just start a new video and continue the problem in the next video. YouTube puts some limit on how long videos can be, and I'm never quite sure what that is. So I'm just going to play it safe, and we'll continue this problem in the next video.